Hello and welcome back to Complex Analysis. And in today's part 27, we will talk about the famous Cauchy's integral formula. However, you already know, before we start, I really want to thank all the nice people who support this channel on Steady, via PayPal or by other means. So thanks for motivating me continuing with these videos. And with that, I would say, let's start. Now, of course, today's topics, Cauchy's integral formula, is related to Cauchy's integral theorem we have discussed in former videos. And indeed, both things tell us that holomorphic functions are in some sense very special. There, please recall, Cauchy's theorem told us that inside such a domain of a holomorphic function, every closed curve gives us a contour integral of 0. In particular, this also holds for a curve that is given by a usual circle. Now, the circle is interesting because it will tell us a lot about the points inside the disk. Indeed, it will turn out that all the values inside of the function f are already determined by the values on the circle. In other words, a holomorphic function does not have a lot of freedom. It's already determined when you know some values on a line. Okay, and now Cauchy's integral formula will make this more concrete. Therefore, let's put it immediately into a theorem. And then the most important ingredient is of course a holomorphic function f. And for the domain, we just have an open domain called D. And then the only thing we demand from the domain is that it contains such a disk. And you know, the disk we can describe with B r z0, where r is the radius and z0 is the middle point. Okay, now the disk should be a subset of D, but we also want more. We want that the closure lies in D. This simply means that the circle here lies also in the domain D. In other words, our circle here does not lie on the boundary of D. So you see, this is not a strong requirement, but we need it because we want to talk about circles. In particular, our curve gamma should be the curve that lies on this circle. More precisely, our gamma from AB to C is the closed curve defined by the circle here in the image. And often, as a notation for the circle, you write del curve D BR. More concretely, this means it's the boundary of the disk. Moreover, you have already learned that in this case the winding number of the curve gamma around z0 is equal to 1. So please remember that, we just go one round around the circle. Okay, so this means the picture of our curve gamma is already here. And then as promised, we can say something about the points z inside the disk. More precisely, I can tell you we can calculate f of z for all points z inside BR. So please note, it does not have to be z0, but also any other point z of the disk. Okay, now f of z is given by the closed curve integral along the circle. And indeed, as a shortcut, one often writes this del BR instead of the curve gamma. But of course, it means the same thing, it means the simple circle given by gamma. So now at this point we have to be careful because z and z0 are already occupied, so for the integration I take a zeta. So in particular, here we will integrate f of zeta. And we divide that by zeta minus the point z. Now, this is the important integral which gives us almost f of z. I say almost because we also have a factor in front. And this is the famous 2 pi I factor we see often in complex analysis. In fact, this is not a surprise at all because the formula also has to work when f is a constant function. So in particular, when we have 1 and 1 here, we get back our usual integral 1 divided by zeta minus z. And there we already know the curve integral along the circle gives us the factor 2 pi I. Okay, now in summary, you see this is the famous formula you should remember, and it is called Cauchy's integral formula. And in fact, with the stuff we have already learned, we are able to prove it. The first thing we use is what we have learned in the last video. There, a function g defined on the pointed disk played a crucial role. So you see, g should be a holomorphic function with one exception point. And now the only thing I want to change from the previous video here is that I want to call the radius r tilde. In fact, r tilde should just be a little bit bigger than r. And it should be chosen in such a way that the whole disk with radius r tilde still lies completely in D. Of course, this is always possible because the assumption said that the closure of the disk lies completely in D. Therefore, inside the open set D, it's possible to enlarge the disk a little bit. Okay, now the only question that remains is, what is the definition of this new function g? And of course, the answer is not a surprise at all, because we see the function already in the integral. Hence, a point zeta is sent to the number f of zeta divided by zeta minus z. And by having this, you should also see that the exception point here is not the middle point z0, but rather the arbitrarily chosen point z. So let's also change that, and then the definition of the function g is complete. Then, in the next step, you immediately recognize what we will talk about is the closed curve integral of the function g. More precisely, we consider the contour integral along the closed curve given by the circle with radius r and middle point z0. However, you already know z0 is not so important, we are rather interested in the point z. And there, please recall from the last video that instead of this big circle here, we can also choose a smaller circle around the exception point z. So this was exactly the result the keyhole contour gave us in the last video. In fact, this was exactly the reason why we talked about this in all detail. So now please note here, instead of the radius r, we have any small radius epsilon here with the middle point z. Of course, the only restriction we have is that epsilon should be smaller than r. Okay, now by having changed this integral here, our calculation gets much easier. And in the next step, we just need an idea how to split up the function g, just that we can calculate this integral. Actually, if you look at the result at Cauchy's integral formula, you might already guess what we can do. So you should see, in some sense, we have to bring the value f of z into the game. And of course, we can just do that in the numerator here by adding and subtracting the value. In other words, we have a big numerator now. So we have minus f of z plus f of z. And then, here in the first part, you should recognize this is just a difference quotient as we often have it. Hence, the idea would be to rewrite this with two integrals. Therefore, the first one here is the one with the difference quotient, and the second one is where we have the constant f of z. So please note, this one now is different from the original integral because the numerator is constant. And in fact, with that, you know, we don't have any problems calculating this integral. Namely, it's simply 2 pi I times the constant f of z. On the other hand, the first part here can be made very small if epsilon is chosen as small. For this, of course, we use that f is complex differentiable at the point z. And then together with the standard estimate for a contour integral, we get our result. Okay, to make this a little bit more precise, let's write it down that the absolute value of the integral above can be estimated with the maximum of the function inside the integral times the length of the curve. And the length of the curve is the length of the circle, which means 2 pi times epsilon. Moreover, now we can use that this maximum here is bounded because you see if epsilon goes to 0, this whole thing here goes to the derivative of f at the point z. Or in other words, since we have this epsilon here, the whole integral goes to 0 if epsilon goes to 0. Or in other words, since we have the epsilon here, the whole thing, the whole integral goes to 0 when epsilon tends to 0. And then you see, this is an important result because it means only the second term here remains. Hence, we can conclude that the integral here along the large circle is equal to 2 pi I times f of z. So in summary, we observed that this is exactly Cauchy's integral formula we wanted to prove. So the proof was not hard at all because we already had everything we needed. Now, as I already told you, this result is very strong because it tells us a lot about holomorphic functions. Indeed, it will imply some nice facts you will definitely remember. However, I would say that's a topic for the next video. Therefore, I really hope that I see you there and have a nice day. Bye!